we're going to be looking at aromatic compounds. These are usually rings with alternating double bonds. And they're very stable, and so as a result, they're common in nature. So a lot of what we study in organic chemistry reflects what we see often in nature. The classic aromatic compound is benzene, which is shown here. I've drawn another equivalent version of benzene here on the right. So these are exactly the same. If you imagine the whole molecule rotating like a wheel, it's easy to see that these are the same. And I'm going to talk a little bit more about the electronic nature of benzene, which explains its unique stability. So if we draw benzene out fully, showing all the carbons and hydrogens, all the implied carbons and hydrogens, we would begin like this. And then we have alternating double bonds. And then we fill in the implied hydrogens in order for each carbon to have 4 bonds. And that is benzene. One thing I can point out even at this point is each of these double bonds has a pair of electrons in its extra bond, if you will. I've called them pi bonds before. You've probably heard that. So this arrangement allows these electrons to circulate around the ring because it's an unbroken conductive wire, if you will, imagine it that way, of electricity, which is electrons. So let's look at that some more. This phenomenon of aromaticity, okay, so is related to what I just said. Benzene, and now let's compare it to something that's not aromatic, like 1,3-cyclohexadiene. So numbering this diene, 2 enes, 1, 2, 3, 4, it's a 1,3-cyclohexadiene. The alkenes beginning at 1 and beginning at 3 in sequence. However, I can point out that these 2 carbons here have their full complement of hydrogens if you fill in to make 4 bonds. So let's take a look at these 2 compared to each other. So as it comes in, hopefully here, there we go. That's benzene, and notice how flat it is. And now here's cyclohexadiene. I'll run through this again. Cyclohexadiene, you notice these 2 carbons in front have the 2 hydrogens on them. That's going to interrupt the conduction of electrons around the ring. So electrons in cyclohexadiene that we're looking at now can't go past those CH2 groups. But in benzene that we're looking at now, look how flat it is. The electrons can circulate continuously around the ring. I don't really have good animation of that, but it would be good to see that. So think about the 2 pairs of electrons in the double bonds. They're stuck where they're at. They can flow back and forth a little bit between those double bonds, but they can't go onto either of the CH2 groups shown in front. And the molecule is not flat because the CH2 groups are tetrahedral, and benzene, as you're seeing, is all trigonal planar all around. So bringing back those geometry concepts again. Okay, you can see the ring is flexed. Okay, so to further explain this, maybe to help remember it by further explaining it, when we further explain things, we remember them better. So benzene, it has these pi bonds all around that form between these orbitals that contain electrons. So each of these orbitals has an electron in it on each carbon. And so if you can actually see the conductive nature of the electrons around the ring, they're all basically identical. Whereas in cyclohexadiene, over here on the right, you can draw in electrons on the 2 double bonds. These can overlap, but then it's broken up by these right here, which are fully saturated carbons. All right, so naming of aromatic compounds. We're not going to go crazy with this, just learn some simple basic naming. One of the interesting and easy to remember really things is ortho, meta, and para, which apply to di-substituted benzene type rings. So meaning a benzene ring with 2 substituents. So if it had 2 substituents, one there connected to something and one there, these are called ortho to each other. So, and the way we would speak it is these 2 substituents, whatever they are ortho to each other, and we might include it in the name of the compound, like ortho-dibromobenzene, for example. I'll show some examples, and I gave you plenty of examples in the book to work on. If they're separated by a carbon in between, like this, they're meta to each other. And if they're separated across the ring on opposite sides, they're para to each other. Then on top of that, there's about a half a dozen or so benzene type compounds that have their own common names, their particular names, because they're so common actually. So these are shown in table 13.2. The ones from that table that I'm requiring are these, which I think leaves out 1 or 2 from the table. Toluene is a benzene ring with a methyl group on it. So it's real common in nature. It gets its own name because it's seen so often. Toluene is the good or bad smelling, depending on your point of view, stuff in model glue. Phenol is a benzene ring with an alcohol on it. So that's easy to remember because of the -ol. But it's not phenyl, it's phenol. There is a different thing called a phenyl, which I probably should mention in a moment. Aniline is a benzene with an amine on it. So amine starts with an A, aniline starts with an A, and amines always end in -ene. So amine. Morphine is an amine. Lots of others. So benzoic acid is a benzene ring with a carboxylic acid on it. And carboxylic acids look like this. We're going to study them in a whole separate unit, but they have this weird oic acid ending. Benzoic acid, real common in nature. I think it's used as a food preservative, if I remember right. Or maybe an ester of it is actually. Benzaldehyde. It's a benzene ring with an aldehyde on it. So that's super easy to remember, as long as you remember what an aldehyde is. When I said a phenyl, so a benzene ring as a substituent. As a substituent stuck to something else. So like a methyl group, an isopropyl group, a tert-butyl group, the ones that we learned. If a benzene ring is stuck on as a substituent, it's a phenyl group. Oops. Oddly, it should have been called a benzyl group, but it ended up being called a phenyl group. So that's just a little side note. Probably good to mention at this point. Here's some naming examples, and there's a lot more in the practice problems I assigned. So this is bromobenzene. That's easy. This is either meta bromo chlorobenzene, right? So B before C, meta, they're meta to each other. So that's how you use the word meta in a name. But equivalent to this, you don't have to use the meta. You can say 1, 3, it would be 1 bromo, 3 chloro benzene. So these are equivalent correct names for this. Here's where what we learned just above applies. So right here you see toluene. So, and then there's a bromine on it. So it's meta bromo toluene. But then again, alternatively, it's still correct to say it would be 1, 2, 3, excuse me, because bromine is higher atomic number and takes precedence in the numbering. So it would be 1 bromo, 3 methyl benzene, if you want it. And that's equally correct, but much fewer people would use it. Most everyone would say metabromotoluene. Again, looking for parent compounds hidden within. The parent compound here is phenol. So this is para-isopropyl phenol. Going back to our alkyl substituent names. Propyl phenol. So you use the parent name if you see it in there. Para-isopropyl phenol, or you could say 4-isopropyl phenol in this case, because everyone knows that the all in phenol would be numbered 1. So you'd have the isopropyl group at the 4 position. But most everyone would call it para-isopropyl phenol. This one would be meta-methyl benzoic acid. Continue down here. So, and you say, okay, well, this could be a toluene, but then what do you call this? So the benzoic acid really takes precedence also because of the atomic numbers being higher for oxygens. So this is a benzoic acid derivative. It's a methyl benzoic acid, methyl benzoic acid. Here we have an aniline. It's not always pointed straight up, right? Chemists don't know up from down or left from right, really, when you think about it. Molecules don't. So this is an aniline. This is orthofluoro. Fluoro, aniline. Or I suppose it's 2-fluoroaniline. But that gets a little funny because nitrogen's higher atomic number. So we can speculate. This is the best name for it, orthofluoroaniline. You could also possibly speculate that it's 1-fluoro 2-amino benzene, giving the fluorine higher atomic number precedence. I think I like this one the best right here. This one second best, and this one I wouldn't use. So we'll just go with that. All right, so this coming week, again, we're done with videos for this unit. There's plenty of reading and practice problems in the book.